Hi everyone, welcome back. In this video, we are going to solve the problem minimum swaps to arrange a binary grid. We will break it down step by step and we will walk through a full example so you can clearly see how the grid strategy works. We are given n by n binary grid and in one step we can choose two adjacent rows of the grid and swap them. A grid is said to be valid if all the cells above the main diagonal are zeros. We need to return the minimum number of steps needed to make the grid valid. Else, we will return -1 if the grid cannot be valid. So we are given an n by n binary grid, and our goal is to rearrange the rows using adjacent row swap only, so that for every row at index I, all the ones appear in columns less than or equal to I. That means the rightmost one in row I must be at index I or smaller. So here is the most important insight in this problem. For any row, we only care about the position of its rightmost one. If the rightmost one in row I is an index greater than I, then this row is invalid, and we need to do some swaps, if possible, until we have a valid row. So to do so, first we need to scan each row from right to left, and as soon as we see a 1, we record its index. After this step, each row is represented by a single number, which is the position of its rightmost one. Let's walk through a concrete example to make this clear. Suppose that we have a grid that looks like, let's say, at row 0, 0, we have 1, 1, 0. Then at row 1, we have 1, 0, 0. And at row 2, we have 1, 1, 1. At this point, we have to calculate the rightmost one at each and every row. So again, at row 0, the rightmost one is at index 1, and for row 1, the rightmost one is at index 0, and for the last row, the rightmost one is at index 2. So now the grid can be represented by an array of these indices 1, 0, 2. At row 0, here to satisfy the requirement, we need the rightmost one to be less than or equal to 0. But row 0 doesn't satisfy this condition because 1 is greater than 0. Row 1 had the rightmost one at index 1, while we need it to be at index 0. So We scan downwards the array to find a valid row. So which one is a valid one? We will see that row 1 is valid. So we need to swap row 1 here with row 0 to become like that. So now the first row satisfied the condition, and the cost to reach this state is one swap. Then we should move to the next row. Row 1 needs the rightmost one to be less than or equal to 1, and this is satisfied here. So the current row, row 1, had the rightmost one at index 1, which is valid. So we don't need any swap here. And the same for row 2, the rightmost one must be less than or equal to 2. And this condition is also satisfied, so no action is needed here. The total number of swaps, or the cost to reach this state, equal 1. And this is the final out. But before moving to the code, there is one case that we have to take into consideration. And that case, when we scan downwards the indices array and we cannot find a valid row, then it is impossible to arrange the grid. And in that case, we return -1 immediately. So for example, here, example 2, in the given examples, we have all the rows are similar. So swapping here has no effect on the grid. So the final output should be -1. And now let's move to the code. First, I'll define a variable n that will hold the grid size. And also I'll define a vector of type int. I name it rightmost one. It will be of size n, and I'll set all of its position to -1. And this is the array or the vectors that gonna hold the indices array, the index of the rightmost one at each and every row. Then we'll move to step 1, which is find the rightmost one in each row. How? We will scan the grid from I equal 0, I is less than n plus plus I, and we'll scan the columns from the first loop is scanning for each row, and the second loop for scanning the columns from right to left. So I'll start by j equal l minus 1 and j is greater than or equal to 0 and minus j. Then I'll check if the grid I and j equal to 1. That means that I reached the right most one. So I'll set that position in my vector and I'll break immediately. And this is the first step. Also here we need to define a variable. Let's call it swaps to hold the final result. Step 2 is, let's name it ready row arrangement. So for each row in the grid, I equal 0, I less than n, and plus plus I. Here we need to find a row where j is greater than or equal I, that satis satisfies the condition of uh, the rightmost one of j is less than or equal I. So let's create another variable j. I'm gonna start from I and looping while j is less than n. Make sure that we are not outside the array boundary and checking that the rightmost, let's copy it, the rightmost one at j is greater than I. In this case, I'll increment the j variable. That means j will keep incrementing until we find a valid uh, a valid indices that make a valid row. So here we need to check for the case where j equal n. This means that we will not be able to rearrange the grid because there isn't any valid row, and here we will return immediately -1. After that, we need to do the swapping while j is greater than I. We will swap the rightmost one at index j with the previous one. And that and moving upward the array or moving it from right to left, and that will cost us one swap. So I increment my output variable. I'm naming it swaps. And finally, I'll return swaps. Let's run it to make it error free. Make sure it's error free. Having misspelled here. Okay, let's run again. Okay, as you can see, all the test cases pass. Let's submit it. And here we go. Finally, you may ask why this greedy approach works. My answer is choosing the closest valid row always minimize the number of swaps. Any row further down or further right uh, would require more adjacent swaps, which would only increases the total cost. And if we have several rows that satisfy the condition for the ice row, these rows must also satisfy the requirement for the second rows because as I increases, the constraints on the number of leading zeros becomes smaller. Finally, in terms of complexity, these algorithms run in O of n to the power 2 n squared time, and it uses an extra space to hold the rightmost ones indices, so that the space complexity is O of n. And this is optimal for this problem. Uh, Thanks for watching, and if you found this explanation helpful, feel free to like the video and subscribe for more coding walkthroughs. And see you in next problem. Bye.